Hello, in today's video we're going to be talking about a type of periodic trend. We're going to be talking about the size in relation to the different atoms that are on the periodic table. So I'm going to quickly draw a sketch of what the periodic table looks like. It looks like this. Looks something like that. So there's our periodic table. And we know that there are two opposing forces in an atom. We have the Z effective. Remember, the Z effective is going to be the positive to negative ratio. So it's positive to negative ratio. So that's basically the number of protons to the number of electrons. And we know that Z effective is going to be your driving force for keeping the electrons close to the nucleus. We also have repulsive, a repulsive force. This is your electron-electron interaction, E interaction. So that is going to be repulsive. We know that particles of like or similar charges don't like each other. They want to be repulsed by each other. So we have these two types of interactions. Now, let's look at the periodic table and let's see what happens as we move from the left to the right and we move from top to bottom on the periodic table and see what the size, or the relative size of these atoms are going to look like. So if we start at the left and we go down, we know that we're going to start adding in protons as we move from the left to the right. You could look at any periodic table. We could see that carbon would be 6, nitrogen 7, oxygen 8. Okay. So we're adding in an electron every time we move, or a proton every time we move from the left to the right. That adds in an extra positive charge. But we also know in a neutral atom, we're also adding in an extra electron. However, so that we have both of these forces acting when we move from the left to the right on the periodic table. Now, going from the left to the right, the Z effective is a bigger force than the repulsive nature of the electron-electron. That's just what the standard calculations show us. That Z effective moving from the left to the right is bigger than adding in an extra electron, which has an extra repulsive force. So as we move from the left to the right, the Z effective is getting bigger. The electron-electron repulsion is also getting bigger, but not as fast. And so what we get is, as we move, so if we look at carbon, we'll have a general size. We add in an extra electron and an extra proton, and we get nitrogen. Now the Z effective is going to be more strongly apparent in nitrogen, which means the nucleus is really pulling into those electrons with a much greater force than it was with the carbon. What that does is makes the nitrogen smaller. You go up one more, oxygen. The Z effective also increases. The repulsive nature increases, but not at the same capacity. So Z effective is bigger. You're pulling these electrons in closer, even though there are more of them, we get smaller. So as we move from the left to the right on the periodic table, we decrease in size. Okay, so now we have one of our trends on the periodic table. Going from the left to the right, we're going to decrease in size going from the left to the right. Great. We're going to be talking about these two forces for a lot of our trends. Now let's see what happens when we go down the periodic table. In this case, we can't really look at this too much because we know that n, the principal quantum number, is going to be changing as we go down the periodic table. So what does that mean? N equals 1, and let's just look at the s orbitals, so the ones on the far left over here. N equals 1 for this. M sub L, or L, is going to be equal to 0, and M sub L is going to be equal to 0, but we don't mind. So this is the N equals 1 shape. We're going to say it has a shape that looks something like that, a size that's relatively looks something like that. We know it's a sphere, it's the L equals 1. If we drop down to the N equals 2 phase, we also know that L can equal 0 or 1, but let's keep into the 0, so the s orbital. As you go down the periodic table, you increase, you add an extra shell. So our original shell was this. This is the n equals 1. Our second shell is going to be your n equals 2. So no matter what, if you increase your principal quantum number, you're going to be increasing the size. So this is going to be increasing. So as we move from left to right, we decrease in size. As we move from top to bottom, we increase in size. So the elements that are down at the bottom part of the periodic table are going to be huge compared to the elements that are at the top part of the periodic table. That is one of the reasons why the elements down here at the bottom of the periodic table are unstable. You'll notice that a lot of the elements in the F orbital branch down here, the part that's not actually added on to the periodic table, these ones, a lot of them are radioactive. That means that they're going to spontaneously fall apart. The reason for that is they're becoming too large. The nucleus of the atom can't hold on to all of the electrons, and they just spontaneously fall apart. So the elements that are up higher on the periodic table tend to be more stable than the elements that are lower on the periodic table. So this is our first trend on the periodic table. You decrease in size going from the left to right. You increase in size going from the top to bottom. I want to talk about ions, and we'll just do a quick ion comparison. Let's look at magnesium. Magnesium has 12 protons, a neutral magnesium and 12 electrons. We know that magnesium's a metal, which means it's going to form cations most of the time. Magnesium plus 1 would be 12 protons and 11 electrons. We've lost an electron. What this means is our Z effective has increased. We now have more positive charge to negative charge than we had up here. That means that this magnesium plus is going to be smaller. The protons are pulling on those electrons with a greater force. Mg2 plus is going to be 12 protons and 10 electrons. Z effective also increased here. That means that this is going to be still smaller. So if we do a relative size comparison, they're going to look something like this. That means that a cation is going to be smaller than its parent neutral atom. Mg2 plus is always going to be smaller than Mg. Let's look at the anion side and see what we see, and see if this trend still holds. So that's for a cation. You decrease in size as you increase in positive charge. If we look at nitrogen, neutral nitrogen has 7 protons and 7 electrons. N minus 1 would be 7 protons and 8 electrons. Now our Z effective, which is the relationship between positives and negatives, has gone down. Keep increasing the negative charge, 7 protons, 9 electrons. Z effective went down here as well. And 3 minus, 7 protons, 10 electrons. Z effective decreased here. So what that means is that as the Z effective is decreasing, the nucleus isn't holding onto those electrons as strongly. So if we do a relative size comparison, the anion will be larger than the parent neutral atom. And that's solely because of the Z effective. The nucleus isn't as able to hold on to all of those electrons. There's too many surrounding it. So it just keeps getting bigger and bigger and bigger. So this is the exact opposite we see with the cations. The cations get smaller, the anions get larger. And with that, that's all I want to talk about with size. We'll be dealing with a lot of different examples of these tomorrow in class, as well as identifying which elements can be affected by a magnetic field and which ones cannot. So with that, I want to say have a great night. I will see you all in class tomorrow.